Hello everyone, welcome to chapter 7 of the pre-calculus course, and this chapter is all about trigonometric function properties, identities, and parametric functions. So last chapter I introduced you to the sinusoidal functions, or the so-called periodic functions, such as the sine function, the cosine function, and some other functions relative to these two primary functions, sine and cosine, which are the tangent functions, cotangent functions, the secant functions, and cosecant functions. Also, we have discussed the other circular functions and solved some equations for which x as a value or angular value could be found using the equations of these sinusoidal functions. For this lesson, we will be more familiar with the different sinusoidal functions and also the other functions I said, such as the tangent function and the cotangent function, secant function, and the cosecant function. So we will begin this chapter with 7-1, Introduction to the Pythagorean Property. So you are already familiar with the Pythagorean Theorem, or the Pythagorean aspect, I suppose. And Pythagorean, the word Pythagorean Theorem was actually taken from Pythagoras, who discovered this type of theorem while he was dealing with lines and shapes. So he said that if we have a right triangle, okay, for example, we have a triangle, and supposedly this triangle is right, and it has its two legs called, for example, it has a certain angle, it's coming from a certain acute angle, theta, for example, then it has its legs, and these legs or sides could be coined as opposite, which means opposite the angle, and also adjacent, which means it contains the angle, okay, or it is near the angle. And we also have the hypotenuse, okay, hypotenuse, or the longest side in this triangle. There are two conditions for the Pythagorean theorem to exist. The first one is that this triangle that we should work on should be a right triangle, and secondly, we are getting an acute angle for the triangle. So he said that Pythagoras said that the hypotenuse, or the square of the hypotenuse rather, is equal to the sum of the squares of the two sides. And this became famous as what we call the Pythagorean theorem in trigonometry as well as in geometry. So the objective in this lesson is to investigate the sum of the squares of the cosine and sine of the same argument, meaning we have an argument x, for example. So this is y is equal to sine squared of x. Now, first let us draw cosine squared of x. So we're going to what do you call this, to draw the same thing as this one. We will draw cosine x. So let's do first cosine x. Okay. And then later on, we're going to sketch the sine x. Okay. Let's label this axis. This is -1. This is +1. This is, let's say, 90. 180, 270, and 360. And this, of course, is our theta axis, or if we have an argument of x, this is the x-axis, which is still in the angular, or which is still the set of angular values. And this is our y. So this has been taken over and over, and we have said that for cosine x, it would start with a high point of positive 1 at x is equal to 0. And then it will be 0 at 90 degrees, negative 1, 180 degrees, and at 270 degrees it becomes 0 again, and at 360 degrees it becomes 1. For review on this topic, you can visit lesson 6, and it will give you a more detailed explanation. Some videos there are worth, detailed than in this video. Okay, so if we're going to sketch the function cosine of x, this is our y is equal to cosine of x. Okay, so this is y is equal to cosine of x. Now, what about y is equal to cosine squared of x? So let's solve that here. We'll just need some labelings. We need a table of x and y values. Okay? So let's say this is our x and this is y equals cosine squared of x. Let's identify these x's as 0, as angles. These are angles. 90 degrees, 180 degrees, 270 degrees, 360 degrees. Okay? Now using our calculator here, we have a scientific calculator here. Let's see what happens for 0 cosine squared. Okay, cosine equals, and then square it, so it will become 1. Still it's 1. And take note here that when you say cosine squared of x, y equals cosine squared of x is also equal to y equals cosine x square. Okay, so these two are similar. So let's say 90, okay? But make sure you are in degree mode. Right now I am in degree mode, so I could compute for 90 here, which means 90 degrees. 90 cosine, which is 0, squared is still 0. Okay, 180, so 180 cosine, it's negative 1, square it, becomes 1. Okay, and what else? We have 270 cosine, it's 0, so it's still 0, and this will become 1. Okay, so notice that we all have a positive for every negative counterpart on the cosine of x. For the cosine of x, y is equal to cosine of x, this is our negative counterpart, which is obtained when x is equal to 180 degrees. But in this particular instance, our cosine squared of x, y is equal to cosine squared of x, will be positive 1 again. Okay, so take a note of that for every negative value for cosine x, we have a positive value for the cosine squared of x. Okay, so if we are going to graph this thing here, then this will be the graph of this function. Will be like this. Okay, like that, and so on and so forth. So take note that y is equal to cosine squared of x is what do you call this, a positive function. Notice that it doesn't have any value on the negative y part. Okay, so for every x values here, it doesn't fall below the negative y value. So our y is equal to cosine squared of x, and this is this function is a positive function. Okay, so this is the value and the sketch of the two functions. We have the cosine x function and the cosine square of x function. So to be more accurate, let's make the cosine function a broken line to give emphasis to our sine of x function. I mean our cosine square of x function. So this is the result. Okay, how about our sine function? So for the sine function, let's start again with the axis. Okay, and have our labels. Okay, so some of the annotations are already ready. This is supposed to be our x, and this will be y is equal to sine x, and the other one would be y is equal to sine squared of x. Now let's see the difference here. So if our x is, again, we will have the same values of x, which is from 0 going to the first revolution, so 60 degrees or 360 degrees. So 0 and then 90. Now you could also use the radian mode here, and to convert this degree mode here to radian, all you need to do is to multiply this degree here by pi over 180, and it will give you the degree version. So this is 180 degrees, and this is 270 degrees, and this is 360 degrees. So at y is equal to sine x, for x is equal to 0, that would give a value of 0. And if we square that, we also get the same value. So we have 0 also for here. If it's 90 for x, then we will have a value of 1 here. And also if we square that here, it will still become 1. So if we have x is equal to 180, that's still 0. 0. And if x is 270, we're supposed to have negative 1 for sine x. But on the other hand, we will have a square of negative 1, which will become 1. And for 360, this is just an alternation of from the 180 degree value. So having done all those, or having gotten all of these values for y, for which x is given, for 0 degrees we have sine x is 0. So this will be the first point for y is equal to sine x. For 90 degrees we have a value of 1 for both. And for 180 we have 0 here for both. And then for 270 we have positive 1 for the sine square of x, but we have a negative 1 for the sine x. And then 360 is 0. So let me just convert this into a blue thing. Okay, this is for the sine squared of x. And if we are going to graph the first function, y is equal to sine x, which is the parent function, then we will get this. We will get this graph here, which is pretty like this one. Okay, this is the graph for y is equal to sine x. If we are going to graph the other function, y is equal to sine squared of x, then we have the same. I'm sorry, this is for the sine x. It has to be like this. Okay, but for the sine squared of x, we will have this function, okay, or this graph. So notice what happens. Should be a little bit. Okay, so it will be like this. Okay, this is our y is equal to sine squared of x. Well, the sketch graph in red here is y is equal to sine x. And to give emphasis to y is equal to sine squared of x, you could just make this a broken line for sine x and see what happens for our y is equal to sine squared of x. Okay, so what is left is this sketch of y is equal to sine squared of x as a solid line. Okay, therefore these are the graphs of the basic functions against their squares. Okay, so for cosine squared of x against cosine x, this would be the graph. And look that it look kind of similar to sine squared of x, such that they don't have a negative value for every value of x. Okay, they will have the x-intercept here, but nevertheless, they will not have a negative value for y. So in this case, y is equal to sine squared of x is also a positive function. Okay? And as you could see, these two values here are alternatingly obtaining a y value of positive 1 for every interval, like for 90-degree interval. Let us take a look at cosine squared of x. At x is equal to 0 and 180, it has 1. And then for sine x, at x is equal to 90, it has a value of y is equal to 1, meaning that it is actually filling the holes within the intervals of 90 and 180, such that if we are going to use a calculator, we will notice that when we add together the squares of both these functions, let's say we have sine squared of x plus cosine squared of x, the answer is always leading to 1. Like, let's say for example, we have 90 degrees. So let's have sine of 90 degrees, okay? So 90 sine, square it, plus 90 cosine, square it. The answer is 1. Okay? So this leads us to a Pythagorean identity for sinusoidal functions, which is equal to sine squared of x plus cosine squared of x is equal to 1. This is a Pythagorean property for both sine and cosine function.